Thank you, everybody. And this is the title of my talk, is the influence of magnetic fields on the kinetic of chemical reaction. This title I chose this title many months ago, but when I started to prepare my presentation, I realized that instead I want to talk of different things, because I found on my desk some manuscript that we prepared together with Emilio, and the months just before he passed by. And I decided to read those manuscripts, and I changed my project of the presentation, and this is the results. I want to speak of the supramolecular structure of liquid water that has been described by many other speakers before me. And especially I want to link this supramolecular structure with non-isolated system out of equilibrium, static system out of equilibrium, non-isolated from the environment. Then I want to discuss the effect of weak magnetic fields on hydration of molecules, and I want to discuss the very tiny exchange of energy and matter in aqueous systems that are very crucial to understand what we know about life. So let me begin just describing very briefly the models of liquid water in order to understand how the thought about the structure of water have evolved during the year. The first one who suspected that water has a non-homogenic structure was Röntgen at the end of 18th century. He described water as a two-structure system, but he imagined a sort like a small iceberg of ice immersed in a liquid structures. But his idea was abandoned with the advent of thermodynamics, because physicists said that whenever a system is described by macroscopic parameters such as pressure and temperature, a system described by the same pressure and the same temperature must have the same phase. It's unbelievable for a physicist to understand what does it mean to have two phases at the same pressure and temperature. Then, in the 50s, Linus Pauling elaborated the idea, proposed the idea of hydrogen bonds. Hydrogen bonds are just a model, it's not a theory. It's a very powerful model able to explain the most of the property of water, but not all the property of waters. But the hydrogen bond model gave birth to a lot of subsequent model. One of the most famous was the model by Stanley and Teixeira. They designed liquid water as a gel made up by molecules which develop hydrogen bonds up to 4 hydrogen bonds per each molecules, just connecting a sort of percolation path inside the liquid. This was supposed to give the structure of liquid water. And this is also the base of all the models of the molecular dynamics. All the simulation that you can find in literature in molecular dynamics on the structure of water are, of course, based on short-range forces and on the hydrogen bond model. But there are a lot of information coming from the experimental physics that were collected for the first time, but I'm not sure it was the first time, but Robinson in the 70s, if I'm not wrong. He described water collecting, he made a beautiful review of the experiments, and he described water as a mixture of 2 different phases, just starting from the empirical observation. He said, okay, in order to explain most of the experiments, we have to say that water is made up by 2 fractions. One fraction having a lower density and another fraction having a higher density. But this was very clear to biologists at that time, because biologists are familiar with the cluster flickering model, because they, in order to understand biology, have to assume that water is made up by clusters made up of low energy, it's a low density state, but this cluster are not long-living cluster, but they flicker in very quick way. Their lifetime is in the order of 10 to minus 12, 10 to minus 15 seconds. This was clear to biologists, is not clear to many physicists right now. But then, when the electrodynamic coherence, the electrodynamic coherence started to be understood and applied also to solid-state matter, electrodynamic coherence was developed in order to understand high-energy physics. But Giuliano Preparata and Emilio Del Giudice started to apply that framework even to the solid state. And this was very fruitful because it allows to understand many behavior of the solid state. And especially, it led to the comprehension of the two-state structure of water. It was proved that, this is a general theorem, whenever a system is made up by many molecules, more than a critical density, and it stays at a temperature that is lower than a critical temperature, it develops, the ensemble of particles is subjected to a collective coherent oscillation between a couple of internal levels of its component, thus generating a collective behavior. This is a very general scheme that is valid in solid-state matter. This collective behavior is responsible for the long-range forces, which account for the existence of condensed state. This is just the long-range forces, which adds up to the short-range forces we are accustomed, we know very well. Water is a remarkable example of such a general principle. It is possible to show that water is a superposition of two populations, one population which is called coherent and another one which is called non-coherent. That means that there are molecules which perform this oscillation between these two states and develop a coherent behavior, and the number of molecules involved in the coherent state depends on temperature. It's possible also to evaluate the lifetime of this structure. It is possible to show that each molecule belongs to the coherent state in a statistical sense for a lifetime that is in the order of 10 to minus 15 seconds. The coherent state represents the lowest state of this oscillation. Is an energy gain for the matter to give rise to the coherent states. Now, this idea was rejected by the scientific community for a long time, but very recently I've been published some paper on Nature and on Science, which show that the evidence of the coexistence of two local configurations that has been interpreted as high density and low density water. This is at room temperature and not at super cool condition as what it has been shown in the past. So after about 30, 40 years, now on Nature it has been published the paper which resumed the proposal of Robinson in the 70s. Then the next item is the non-isolated systems out of equilibrium. We have seen during this conference many examples of non-isolated systems out of equilibrium that are the nano-aggregates from Professor Alexander Konovalov and his group, the easy water from Jerry Pollack, the aquaphotomics from Rumiana Tsenkova, and the stable aggregates of water at room temperature shown by Vittorio Elia. These are all examples of stationary systems out of equilibrium, not isolated from the environment. But we are talking about life, because life has all these characteristics, all these features. Now, let's understand which are the parameters important to describe this system. The first one is the temperature. We know temperature, we know from ab initio calculation of QED that water is a superposition of two populations described, and the amount of coherent state is a function of the temperature. But we know also that the contact with surface can move this equilibrium. It can increase the amount of coherent state or decrease the amount of coherent states. The contact with surface, as we see from the work of Pollack, Konovalov, and Senkova, means to stabilize somehow the coherent part of water. But we also heard now that the exchange of low amount of mechanical energy with the environment can stabilize again the coherent part of water. And we will see in the following that also the electromagnetic fields can exchange energy with water, changing the amount of coherent, the ratio coherent, non-coherent water. Just very briefly, what is a coherent domain? It has already said, but just to have a picture, imagine that gases are fully non-coherent systems, because each molecule moves all around, and it just is subjected to thermal knocks. This is the only kind of interaction that molecule gas have. Liquids are systems where electron clouds are coherent. Solids are systems where nuclei too are coherent. This is a general scheme of thought. I don't want to go deeper inside this description because others before me have done it. What we know from the first principle calculation is then the fraction of coherent water is determined by the temperature. Now let's have a look on the surface of solutes in water, or what is the same, what happens on a wet surface. Now we have to come back to another old theory, that is the general theory of the van der Waals forces that has been developed in 1961 by a group of very clever and fantastic, wonderful Russian scientists, the group of Lev Landau. In to these groups belong scientists such as Dzhalodzinsky, Pitaevsky. It's the very top class level of the physics of the 20th centuries. And they approach the van der Waals forces from the scratch, just from the beginning. The basic idea of the theory is that the interaction between non-polar bodies is considered to take place through a fluctuating electromagnetic fields. So the van der Waals forces are electromagnetics in basic. These fluctuations are all spectral components which have the wavelengths large compared to the atomic dimension. Each corpse has its proper absorption structure of the light, is characterized by a spectral signature. This signature influences the forces, the van der Waals forces, which this corpse feels. All the properties of these long wavelength fluctuations are completely specified through the complex dielectric permeability of the body. The only limitation to this theory is the characteristic dimension of the body that must be large compared to the interatomic distances. And this normally applies to all the macromolecules involved in the biological reaction. So this theory is a good candidate to describe the interaction in biological systems. Now, what happened? I don't want to go into the detail of the formulas because I'm not able to do, but what is important to understand? Let's consider forces between two bodies separated by a medium. The forces depend on the dielectric constant on the two corpses, and what is very important, it depends on the characteristics of the medium which fills the gap. We are used to consider two corps separated by vacuum. When we want to understand the interaction, usually we calculate the forces between two separate particles, atoms, or separated by vacuum, because it's easier to manage the equations, but it's not the correct vision. The correct vision is to take into account what is the medium inside. So what we learn from this, that the force is proportional to the distance to -3, but it's also proportional to a very complicated function of the permittivity. The permittivity is the electric constant function of a frequency. And what is important is that it's a complicated function of the differences between the permittivity of the corpse and the medium that is inside. If we are used to manage this formula here, that is a classical London formula for the van der Waals attraction, that is the same formula, but it's obtained in the case when the bodies are very rarefied and the electrical permeability is close to 1. So it's a simplification of the most general formula. What is important to understand? That the attraction and repulsion depend on the medium which fills the gap. So it's crucial to understand the real nature of the medium. And the force can be attractive or repulsive depending on the sign of the difference of the permittivity of the bodies and the medium which fills the gap. So the bodies can, it is possible. Let's assume a reaction in water. We have two bodies which feels we are subjected to the van der Waals forces inside the water. They attract because they have a permittivity such that the sign of the difference give a force greater than 0, so the bodies will attract. Then the short-range forces come into the play. There is a chemical reaction that happens and modifies the spectrum of absorption of those corpus, and the force became repulsive. So we can have a very dynamic concept of the forces. The same force is attractive at the beginning of the chemical reaction and became repulsive when the chemical reaction has happened. Now, let's come to what we are interested in, what happens in water. Two atoms in water. This is a calculation. It was done by Pitaevsky in 5 minutes? No. No, okay, sorry. In 1959. What happens if we have two atoms, two molecules, two corpses in pure water? The formula, as usual, is very complicated. We are not so, I'm not so clever in mathematics to understand detail, but what can I understand is that now I have the forces that is proportional to the inverse square of the electric constant of water. Here. So this complicated formula tells us that we have to have in mind the permittivity of the two corpses, and for small concentration, the dielectric permeability of the two corpses differs very little from the pure solvent, in this case from water. So which left is that the energy or the force are proportional to the inverse square of the dielectric constant of water. So who dominates the formula is water, is the interposition medium. Then we see that when dissolved molecules interact strongly with the solvent, the interaction forces between them are no longer determined by their polarizability, but depend on the electric constant of the solvent. Now, water, because water has a double structure, it has a dielectric constant. The experimental value of the electric constant is just an average between the dielectric constant of the non-interacting dipoles, that is the non-coherent part of water, that can be calculated because they are dipoles, so it's quite easy to do the calculation, and the calculation gives 12. And the coherent domain, which has a very high dielectric constant. It's also possible to be calculated from first principle. So we have this funny situation. When we have to put the dielectric constant inside the formula, inside that formula, which one of the dielectric constant? This one or this one? Now, let's come to a practical problem. The aqueous solution used by Professor Konovalov, they have a typical absorption line in their spectrum that is in the range of 200, 600 nanometer. It depends on the solute. Hence, whenever the average distance among the particles exceeds such a length, this formula holds. You can see here that we have the dielectric constant of water. This is the energy in function of the distance between the two molecules. So energy is decreased by the formation of aggregates of coherent water, because coherent water has a very high dielectric constant. So it is an energy gain for the system to gather coherence domain in between the two molecules of solute. So this can provide a theoretical basis to the formation of the nano-aggregates. Then, this is the formation of the nano-aggregates, but these nano-aggregates must be stable, because we know that they are stable. So this might be the role of the magnetic field, which can have a function of, to favor the pile-up of the energy, aligning the magnetic dipoles associated to the coherence domains, thus stabilizing the aggregates, which otherwise are destroyed by the thermal noise. This is a very rough sketch I did in a hurry. So let's imagine these are the solute molecules inside the solution, and these balls are the coherence domain. They are not in scale, of course. The coherence domain are not round, they have not round shape. They are something like a potatoes, but it doesn't matter the details. So when the distance is less than lambda, and lambda is a typical length of absorption of the substances, depending on the substances, this is the situation. But whenever the distance is greater than this amount, depending again on substances, this situation is favored from an energetic point of view. This could be the explanation of why only 75% of substances shows the formation of nano-aggregates, and why the concentration where nano-aggregates have been measured is different from different substances. I suggest that it could depend on the main spectral absorption line. So the observed stable nano-object has a size of 100 nanometers, which is in the same range of the wavelength characteristic of the spectrum of the solute. So we suggest that whenever the dilution exceeds a certain threshold, where the average distance among solute is greater than the lambda, water coherence domain gather to form a mesoscopic region in order to decrease the free energy of the system. Stable cluster may have a permanent electric charge, as we saw in the previous talk. In fact, it is possible to measure, Professor Konovalov measured the zeta potential that is related to the amount of charge at the border of these structures. This is due to the quasi-free electron at the border of CDs. The reason why we are not able to see this feature in bulk water, it is because the lifetime of CD is too short to be observed. So we need a stabilizing mechanism in order to observe the structure. So we are talking about the arrangement of extended structure formed by water coherence domain. It is also possible, in principle, that water can modify its oscillation in order to further minimize the energy. This implies that water can shift its oscillation frequency, or what is the same, shift the energy gap. This is in principle possible. Okay, it's in principle possible because the electromagnetic EV spectrum of water is very dense of states. So water can choose different states between two, oscillates between one to another. It's a characteristic, it's a typical characteristics of water. So in principle, it's possible. But we have some hints that this could be possible. And these are the blue shift of the infrared spectrum of easy water that has been measured, and aquaphotomics, because we know that water may change its structure after the contact with a solvent. And this is what I've told applies to large distances. At short distances, mathematics diverge because the function becomes more and more complicated. It is possible, but I'm not able to do. So now, come quickly to the easy water case. What happens when a film of water is on surface of a solid body? The chemical potential of the film per unit volume is again a complex function of the permittivity of the solid surface and of the water again. Again, for large thickness, is proportional to R to minus 4 with a coefficient which depend on the electrostatic dielectric constant, and the function of this energy per molecule depends on the sign of the difference of the permittivity of water minus the permittivity of solids. This could open the way for a theory for easy water. Why? Because these are the permittivity of water. The lowest is the permittivity of very dry naphthalene. It's very small. You see here is about, what is 4.5. The average permittivity of water, static constant of water, the average is 80. I remember it you. But what happens? When the naphthalene is hydrated, it starts to increase its permittivity up to a point when the permittivity of naphthalene becomes greater than the permittivity of non-coherent part of water. At this point, the naphthalene became very hydrophilic with respect to the non-coherent part of water. It sucks a non-coherent molecule inside. This is well known because the part of fluoride chain of water are able to fix and to bound many molecules of water. So water enters into the naphthalene and make a chemical bond, making a chemical bond. And this is another rough, very rough and imaginative picture. Dielectric constant of coherence domain is 160, so it's very great. And naphthalene is hydrophobic with respect to this part of water. This part of water, that is the non-coherent part of water, has a dielectric constant that at a certain point became less than the dielectric constant of naphthalene, so it enters inside. What happens is that coherence domain remains on the surface, so naphthalene acts just like a phase separator. This is a very rough scheme, but I think in principle it could be a way to go to understand what is naphthalene. Now, the effect of magnetic fields on hydration of molecule, I've prepared some example to show, but I have no time. It doesn't matter the details of the experiment. We can go quickly. This is important. So, we have shown, and not only we, have shown that even very weak magnetic fields can have an influence on solution both of organic and not organic molecules. So a solution may be influenced by low energy content magnetic fields. So we come to the energy-matter exchange in aqueous system. The spontaneous evolution of a system is influenced by environment, and we saw temperature, energy exchange, magnetic fields, and we can say that the system doesn't reach the thermodynamic equilibrium unless the system is isolated. In any way, it's possible that the system is stable if it is in contact with the environment. And this principle is not only valid for life, but it's only valid for inanimate matter. These considerations have been the basis of an experimental work of an Italian chemist, that is Giorgio Piccardi, who observed that his chemical reactions are influenced by many, many things. The weather, the planetary influences, the moon phase, and so on. But it has not the theoretical scheme, because he worked at the end of the World War II in 50s, 40s and 50s, so he had not the general scheme. Then we suggest that the water is the medium in which this exchange at very low energy occur, and is the medium that is necessary in order to keep all the things in our universe connected one to the other. Thank you.